Sorry about that. So next talk is given by Russell Landry.
And the top button laser? Yeah. All right, there it is. All right, good morning, everyone. My name is Russell Landry, and I'm a research physicist at the Air Force Research Lab. And I do a lot of work with data assimilative ionospheric modeling. So I thought I'd present on some recent efforts to assimilate oblique ionospheric soundings into some data assimilative models. The question comes about why does AFRL care about ionospheric modeling? And we touched on this yesterday, but one of the reasons why is because of HF technologies. So radio waves in the HF band from 30 to 30 megahertz tend to refract as they pass through the E and F region ionosphere. HF technologies leverage this by bouncing signals off the ionosphere and achieving a much larger range than they would otherwise with direct line of sight. So if you want to, these sorts of technologies are highly dependent upon the state of the ionosphere and are very much impacted by ionospheric variability. So if you want to predict the impact of that variable ionosphere on your HF system, you have to model it. So to model it, you need some kind of HF, oh, whoops, let me go back. This only seems to be going forward. There's a smaller button. Okay. So that's, okay, there it is. All right, thanks. Yeah. So yeah, you need a HF propagation simulation, or a ray tracer, and then you need an ionospheric model in order to simulate that HF refraction. So with a sufficiently complicated model that captures all the variability that's impacting your system, you can then accurately predict the sorts of frequencies you can use your HF system and what kind of ranges you can achieve. So IRI is actually a sufficiently complicated model for a lot of applications, but for many applications, it's simply not accurate enough. So for instance, IRI tends to be very biased during solar minimum. It doesn't capture geomagnetic storms. It intentionally averages out the effect of solar rotational period on the UV spectra. It doesn't capture thermospheric effects like gravity waves, planetary waves, thermospheric tides, and it doesn't even pretend to do a good job in the high latitudes. So we want a data assimilative model that can represent the ionosphere or ionospheric variability more accurately. And one of the ways of doing that is to assimilate ionospheric measurements directly into a specification of the three-dimensional distribution of electron density. The best observations that we can use for that are ionosonde observations for ionospheric soundings. So this slide isn't meant to contextualize the problem or talk about the importance of the science on some kind of technology. This is actually an anchoring slide. This is the most important slide of the presentation because the application actually sets all the parameters of how you design your data assimilative system and what kind of observations you should be assimilating and what kind of metrics you use to test, evaluate, and validate your model. So first kind of observation is vertical incidence soundings. We've talked about this yesterday. You have an ionogram here on the right. So a ionosonde will have a co-located transmitter and receiver, and thus it will be receiving signals that, at least in the mid-latitudes, are approximately coming from zenith. And what you get in this ionogram is a series of group delays as a function of frequency. For any particular frequency, that group delay is going to be an integrated function of your electron density up to the height of reflection. But if you take the collection of frequencies, you can invert that into an electron density profile. So if you want to do this in real time, if you want to have a real-time ionospheric model, then you need to automate this process. A human can extract this information, but they're too slow and too expensive. So ARTIST is an example of an algorithm which can extract data from an ionogram. But this is an image processing problem. So the failure rate of ARTIST and any other algorithm like it tends to be pretty high. And when it fails, it tends to fail pretty drastically. So for instance, if ARTIST confuses this FOF1 cusp for the F2 cusp, then you can get an electron density profile that is truncated at something like 180 kilometers, and the plasma frequency, the maximum, is maybe half of what it should be. And the electron density profile that you then try and feed into your data assimilative model will be so different from the background that your model might struggle to actually assimilate it. So it's actually worse than a garbage in, garbage out situation. You can actually have an iterative model that's trying to converge on a solution, diverge from the truth, or perhaps hang or crash or something like that. So quality control is actually one of the most important aspects of this automatic data extraction. So another type of observation that we want to use is oblique ionospheric soundings. So a cartoon of that is given on the bottom left. You have ionosons. Oh, hold on. There it is. You have ionosons on the left and the right, and they're sounding the ionosphere above them. But then halfway in between, you have an HF receiver, and that's going to receive oblique signals from these ionosons, and that's going to give you information about the ionosphere halfway in between. So what you get is an oblique ionogram shown on the right. And this ionogram has all the same information that the vertical ionogram has, but it's a little bit more complicated. But you have E region propagation on the bottom, F region propagation, and then multiple hops. And the goal here is to extract information from this ionogram automatically. So there's an example of a couple of algorithms we're working on in order to do that. And on the left is a machine learning algorithm, which tries to separate out the modes of propagation from the ionogram. So the oblique ionogram shown on the top left here. Whoops. All right. And then on the middle, you have what the machine learning algorithm masked as the F region propagation only. And then on the bottom is the E mode propagation. So this is important. If you can separate out these modes, then you can feed that into an algorithm which is attempting to trace out these shapes, and it won't get confused as to what mode it's looking at. So an example of an algorithm like ARTIST that's working for oblique ionograms is shown on the right. I don't know if you can see the red and green lines here on the bottom, but those are trying to trace out the F region propagation mode. That's ordinary and extraordinary for red and green. And from that information, you can similarly invert that to get an electron density profile shown on the bottom left. This is a 24-hour history of a particular oblique signal. And then quality control is important. So another algorithm we're working on here is called VICES, or Vertical Incidence Sounder Expert System. This takes the output of ARTIST, which extracts information from vertical incidence soundings, and then tries to throw out all the bad analyses. So the top plot here is FOF2, or the peak plasma frequency, as a function of time as extracted by ARTIST. And the black dots are all the observations. And you can see the diurnal cycle. FOF2 is low during the nighttime, high during the daytime. But you also see a whole lot of observations at right about 7.5 megahertz. And that's not a real ionospheric feature. That's a repeated mistake made by ARTIST over and over again. And this is a particularly nefarious form of error because, as you can see, more than half the observations during the daytime are erroneous. And we typically think of or incorporate errors into our data assimilative models by making some statistical assumptions like normally distributed, zero mean, independently distributed over time. But this violates all of them. So these observations they have some normal distribution of error from resolution restrictions, but then you have this second mode of error. So it's not normally distributed, it's not zero mean, and it's correlated in time. So you really want to get rid of as many of these observations as possible. Otherwise, you have to incorporate some very complicated information into your error matrices. So you can see the red line is what ARTIST lets through. And there's a few times during this several week period where it lets in maybe one bad observation, but by and large, it's actually removing something like 95, 99% of these bad observations. So this is incredibly necessary in order to actually have a data assimilative model provide any skill over IRI. If you have a model that just assimilates these ARTIST output, you're going to have a model which fails compared to IRI. In that, half the time it'll do better, and the other half the time it'll be very much worse. So how do you assimilate these ionospheric data? How am I doing on time?
About 9 minutes, 10
Okay.
minutes.
So there's a collection of models. This is just 4 examples. This isn't exhaustive of data assimilative models which can assimilate electron density profiles. So the first approach of data assimilation is typified by IDA4D and NWRA's Northwest Research Associates GYPSY model. And this is actually a lot like NOAA's GLOW-TEC model. It has a three-dimensional electron density field and then modifies that field to account for your observations. So you can just feed the electron density profile into these models. And you also want to assimilate the peak frequency and height as a logical constraint on your vertical profiles or vertical structure. And that's typically the most direct approach, but it's also the approach that's most prone to having sensitivities to bad data. The second approach, which is something that's typified by IR-TAM, is to this is, if you guys remember from the pi-IRI discussion yesterday, IRI models the vertical structure as a parameterized curve, and you have a few parameters that are concerned with the F2 region, so FOF2, HMF2, usually a width parameter. And if you extract just that information from ionograms and then assimilate that, make predictions as to what those parameters should be in space and time, and then feed them back into IRI, you can have a much simpler interpolation or simpler assimilation scheme, which makes your model more resilient to bad data. So one of the things IR-TAM does when they assimilate these parameters is they pass it through a low pass filter. So you get rid of the occasional anomalous bad artist analyses. Now, in the previous example I showed, IR-TAM is going to do a very bad job here because more than half the data is bad. So if you pass this through a low pass filter, you're still going to get a bad analysis. But it does a lot better than IDA4D or GYPSY would do if they assimilated the artist output. So that's one example of a model which changes the way it assimilates data in order to account for the observational bad analyses. Another example is Boston College's RIPE model, and you can consider this a regional IR-TAM. And an example of that is shown on the right. This is a 1 hour of data assimilation. I'm showing FOF2 over the continental United States. All the white circles are ionosons or oblique incident soundings that are going into this model. There's a third approach that you can use to assimilate ionoson data. And as far as I know, GYPSY is the only mature model that can do that right now. And that is to directly assimilate frequency and group delay information from your ionogram with an internal ray tracer into your model so that you don't actually have to make any assumptions on inverting your ionogram into an electron density profile. And it's generally a lot easier to just pick out a few points from your ionogram than it is to trace out that entire shape. So I think that's it. Yes, so to summarize, HF propagation simulations are useful for predicting the performance of your HF technologies. And you really want to know more about the bottom side ionosphere, and that requires direct information if you want to get a vertical structure that's reasonable. So ionoson data is an obvious candidate. You have to get over a lot of quality control issues and with the automatic data extraction. But the main takeaway I want to have from this talk is that you don't want to black box your observations. You don't want to consider observational error to be somebody else's problem, and you're going to just develop your data assimilative model in a way that they specify what the error is and that's it. Because you can have very complicated modes of failure with automatically extracted data, that if you can incorporate that knowledge into the development of your data assimilative system, you can overcome a lot of those problems and actually provide scale over climatology. Climatology, excuse me. I think that's the last slide. Yeah, thanks.
Yeah, thank you for staying on time.
First of all, awesome presentation. Thank you so much. 2 questions. Well, one suggestion, you have to add approach number 4 for anchor.
Oh, yeah.
And so question about your quality control slide. The HMF2 many points on the bottom, is that the contribution of F1 layer that?
Yeah, that's probably mistaken analyses that are thinking the F1 layer is the F2 layer, or at least that's the rule that's triggering those ionograms are being thrown away.
Are you considering contributing this approach to the whatever the future ionosphere provider will be, so they can incorporate this IA method?
Right. So this is a model which hopefully will be made open source. At least that's something I'm pushing for. This is an expert-based system. So if you can release it to the community, then you can get a lot more eyes on that system, and perhaps they can push updates, and you can get a overall better system. And that, I think, provides a lot of value to the DoD.
Thank you.
On the third method of the gypsy assimilation, can you talk a little bit about what they use for quality control and how they do quality control?
Oh, right. So in this case, the observational errors would be, let me pull up an ionogram here. So if you, the vertical. So let's imagine you had some algorithm which picked out data points here. You would usually provide to the ray tracer some kind of information about what the mode of propagation was. If you fail to do that, then you're going to have convergence issues. It's going to be real nasty. So that kind of quality control for gypsy would be something we haven't yet looked into, but that's where the model itself, having some adjustments, can really come in use. So NWRA has been developing a approach called adaptive uncertainty, where they look at the anomalies from their background field and then try to adjust or increase the observational errors in order to mostly just increase the stability of the model, so that you go back to garbage in, garbage out instead of garbage in, disaster.
Yeah, that's I think the way. I mean, that's going back to the tropospheric, where we look at background error, 3 sigma or something to that effect. Yeah, okay, that makes sense. Thank you.
So just the bottom side of here, there is a new technology being developed, GNSS reflectometry, that is using dual frequency reflection measurements over low wind speed sort of conditions, and they're getting coherent phase. So that would be a point where you would have a two-way path through the ionosphere that might be valuable and an interesting operator to put into this.
Oh, and that's over the ocean as well, I'm guessing.
Yeah,
yeah?
exactly.
Okay, yeah.
I have a question too about the gypsy. Yeah, that was I was really interested in that, the direct measurement, and it sounds like it's still somewhat early. So have you had a chance to compare that to the IDA 4D?
Oh, right. So so there's been some research assimilating CODAR information, where you only have the one frequency in the group delay, and they were able to show skill over climatology with just that data alone. But I haven't seen any comparisons of IDA 4D assimilating electron density profiles versus gypsy assimilating the range or group delay. So,
Yeah, one quick question here, Charlie Powell, Space Force. It sounds like your knowledge of obs errors primarily used for quality control. Could you also use that knowledge for just directly assimilating through sort of non-independent observations, and just have off-diagonal elements in your sort of R matrices or your error observation matrices?
yeah, so if you can have some kind of model for how the temporal correlations of your observational errors are evolving with time, then you could change your observational error matrix during the daytime in this sort of situation, but then go back to something that's diagonalized during the nighttime. That's an approach that could work, but if you are able to identify the circumstances wherein most of your data is bad, you could also just not assimilate any data during that time period. So that approach, although promising, is also very complicated. So first step would be just throw the data out. And then if you can get some appreciation of the how to handle those errors in a statistical fashion, then you can start to incorporate that into your models. No.
Well, thank you very much. And I think we'll move on. I see, Dan, you are online. Is Dan going to be running remotely, or are you running from here?
I can do it either way. Which way would you like me to do it? I can share my screen.
Yeah, if you can run it remotely, that would be great.
Yeah, go ahead and take charge remotely, Dan.
Okay.
Dr. Hodis.